Woohoo! Go Bearcats!
Good evening, Bearcats. I hope you're having a fabulous weekend, and I look forward to starting off and continuing in our next unit when I see you tomorrow. Okay, tonight we're going to do 3.1, Day 2. Before I get started, I want to give a shout out to Bach Lau for his fabulous remix video he created last week, which spurred on a few others to also compete in that area. So anybody liking to go out there and do a little sort of video thing, I'll be happy to try to post it within one of my lessons. Anyway, hope you had a great weekend, and let's get started. Tonight we're continuing exponential functions and their graphs. We're going to start tonight by talking about a base of an exponent. Remember last week we talked about exponential functions, and their base was what changed. The exponent is actually the variable. And so we had base 1, base 2, or base 3. We could have a half base. The base could not be 1 and the base could not be 0. It could be between 0 and 1, a fraction, and if it was a fraction, a positive fraction, then it was decay, and if it was greater than 1, then it was growth. Tonight we're going to talk a little bit about a base called base E. It's a number called E. We're going to see very often in nature, in a lot of our applications, that nature require the use of an exponential function whose base is this irrational number symbolized by the letter E. So E is an irrational number, sort of like pi is an irrational number. It's used so often it's given its own letter, base E. Base E really, as you can see here, as you can see right here, base E is really 2.71828, etc., etc., etc. It's a non-ending irrational number. The number is called the natural base. The function is given by f of x equals e to the x. E is just really the base. So you technically could have written this as f of x equals 2.718 dot 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 to the x power. But this is such a special number, sort of like pi, that we give it its special letter called E. It's also got a special button on our calculator as well. Be sure that you see that for the exponential function e to the x power, E is the constant. Okay, it's a constant. It's not an exponent. X is the variable. E is the constant. It just happens to be an irrational number. Here's just a look at the graph of base E over here, very similar to base 2 or base 4 we looked at last week. It's very, very similar. It's been calculated, and notice it still shares that key point from the base graph of 0, 1. Let's move on. Applications is the other thing that we're going to talk a lot about tonight, so we're going to discuss our applications. One of the most familiar examples of exponential growth is that of an investment. When you invest something and it can, the earnings are continuously compounded, the interest is continuously compounded, or it could also be compounded monthly, biannually, annually, daily. There are different compounding methods. We're going to use exponential functions to find our compound interest. Here are the two major interest formulas that you will need to know for the next test. I will not give these to you. You will need to know these. These are not new. You did go over these last year. I just want to talk about this. This is for n compounding per year. Okay, n number of times per year. So in this first one, A is the amount. So I'm just going to identify the variables right here. This might be something good for your notes. The capital A is the amount or the value of the account. So it's the amount over time, sort of like your Y value. It's the output after time and interest has been applied. P is the principal or the initial amount. Often this is the amount that you invest or the beginning amount of something. If it's decreasing, then it's if it's decaying, let's say it starts at a particular value and it decays or decreases over time, then or depreciates would be another way to put that. That is your beginning amount or your initial amount. R of course, is the rate. And please pay attention that the rate must be written as a decimal. Look over here at this study tip. So, for instance, if it's 6%, you must write it as 0.06. You can think about Beyonce's song, To the Left. You take your percentage and you go left, left, twice to get to your decimal. So often you'll hear me say that in class. And finally, or not finally, but E is the base. So that's not really an exponent. That's just the base, and that's a calculator if you're talking about the second one. In the first one, we covered the R, and now we need to cover the N. N is the one that you often get mixed up. N is the number of times compounded. All right, and that's twice in your problem. It's underneath the rate, and then it's also multiplied to the time, and that would be the daily, the monthly, the weekly, etc. And finally, T, so I'm running out of room, is time in years. All right. In the second one, the compounded continuous, this is only used when you're compounded continuous. Then it is the same. A is still the amount or the value of the account over time. P is still the principal amount. R is still the rate. T is still time in years. But E now is the base that you use instead of creating this base of 1 plus R over N. All right, make sure you have those notes written down. Make sure you have the formulas. Make sure you know you've identified each of the variables. You can do it like I did here, or you can just simply write the formulas and, draw out from the side time in years. However you want to do it for yourself, but make sure you understand what each part of those formulas mean. All right, we're going to move on and look at 2 examples tonight. The first example we're going to look at is compound interest. Compound interest, and we're going to look at this problem when we compound our interest quarterly, monthly, and continuously. The first 2 will use the same formula. The last one will, of course, use our formula with our base in it. Our Pert formula is often referred to. So let's take a look at this. We have a total of $12,000 is invested. That's going to be our principal amount. And it's invested at an annual interest rate of 9%. We're going to immediately cross that out and put 0.09, and that is our rate. We want to find the balance, so we're looking for our amount after 5 years, which is T in times. If it is compounded, okay, if it's compounded quarterly, quarterly would be 4 times a year. If it's compounded monthly, that would be 12 times a year. And then, of course, if it's compounded continuously, we're going to use a different formula. So let's do A and B first. All right, let's look at A. So we are looking for the amount. If $12,000, and I'm just taking this straight from our formula, 1 plus the rate, which is 0.09. Compounded quarterly would be 4. And it would be raised to the 4, and then time in this problem is 5. So actually 4 times 5 would be 20. You would want to go ahead in your calculator. You would want, this is the first time we've used our calculator in a while. You can use your blue one even. We would go ahead and figure all of this out first. So if you're using the blue one, it'd be 0.09 divided by 4. Get an answer, add the 1 to it. Raise it to the 20th power, get an answer, then multiply by the $12,000. Be really, really careful how you enter this into the calculator, because that's where you often will make your mistakes. All right, this will be approximately, once you've entered it in your calculator, $18,726.11. All right, let's see what happens when we compare that to monthly. So this is happening 4 times a year. Our interest is happening 4 times a year. Let's see what happens if we happen monthly. Same formula. We'll still have the amount, $12,000. Still have 1 plus 0.09, but this time it'll be compounded monthly. So 12 times a year. And it'll be 12 times 5. And 12 times 5, I believe, is going to be 60. And so again, we'll put that in our calculator very carefully. I would put 0.09 divided by 12. I would enter. I would add 1. I would enter. I would raise that to the 60th power. I would enter, and then I would multiply by the 12,000. Then you're all keeping it all in the calculator, but you're not trying to put it through with a bunch of extra parentheses. So if you do that, you're going to get approximately $18,788.17. Notice, if we're making a comparison between these two, that this is more. This is greater value. So we can come to the conclusion that the more times something is compounded, then the greater the value becomes over time. So it grows quicker. So if that's true, then if we compound something continuously, it should even grow quicker. Using the same information, let's use the Pert formula. So that's P equals, A equals PE to the RT power. And so again, we want to know the A value. Our principal is still 12,000, except we're going to use base E instead, and we're going to have the rate, which is 0.09 times 5. When we put this in our calculator, this time you're going to put base E in your calculator. You will need, I'll have to look. I'm not sure your blue calculator has base E. We'll see. If it doesn't, then we'll use the graphing ones. You'll put the base E in the calculator. You'll raise it to the 0.09 times 5. So you'll raise it to all of this together first. Then again, multiply by the 12,000 last. When you do that, you should get approximately $18,819.75. So again, it's growing faster the more times it's compounded. The more often, I should say, it's compounded. All right, let's look at one more last problem. It's kind of a short night tonight, and this is on half-life. This is on half-life. I'm going to pause for just a second. Half-life is something you've probably done in chemistry before. For some reason, they use a little different formula. I believe this formula is a really simple formula to use, and I really like this. This is one I would keep in my notes for chemistry as well. Seems to be a little bit less complicated. All right, let's take a look at this example. This says in 1986, a nuclear reactor accident occurred in Chernobyl in what was then the Soviet Union. The explosion spread highly toxic radioactive chemicals such as plutonium over hundreds of square miles, and the government evacuated the city and the surrounding area. To see why the city is now uninhabited, okay, it is currently uninhabited, consider this model, which represents the amount of plutonium that remains. And plutonium does have a half-life, and its half-life is actually 24,100 years. Okay, so that's the half-life of plutonium. I want to talk about this formula before we go on and calculate it. P is the amount that remains after year. P in this particular formula stands for plutonium. Often you'll see me write A because it's the amount after time, and you'll see me write P for principal like we did before, but really in this case it would be the initial amount of plutonium that you started with. Multiplied times 1/2 would be the base. It is decreasing, so that would be decaying. And then you're going to raise it to the number of years, so the time in years, over its half-life. And in this case, the half-life for plutonium is 24,100. And that would be different per, depending on what the particular chemical or compounder was. I guess plutonium's an actual... Alright, from the initial amount of plutonium. Alright, we're going to just take a look at what happens in the graph over there. They had substituted everything in, depending on, again, like I said, whatever the particular compound is that you're using. And I don't think it's called a compound. That's really bothering me. So tomorrow in class, if you watch the video, write on your paper. Don't tell me out loud. Write on your paper, and I will come around and look and tell me what all those items off the periodic table are called. Elements. I'm sorry, an element. I just remembered. Okay, you can write elements on your paper anyway, or tell me when you walk in the door tomorrow. Say the word elements to me and we'll know what that, I'll know that you watched the video. Okay, anyway, let's move on. So let's take a look at what happened over here. If we plugged in different points in time, this would be years of decay. So it would take almost 100,000 years. It would actually, to get to maybe half of the original, or I'm sorry, it takes almost 24,000 years to get to half of the original. It would take 100,000 years to get below one what was the original pound, below 1 pound from the initial amount of 10 pounds. It would take almost 100,000 years. That is why that city is still uninhabited, because there's still too much radiation in the area. All right, really this is a great formula to use. I would label it, you know that's time in years. This is the half-life of the element that you're talking about. Like carbon-14 and different things have different half-lives, and if you know that half-life value, then you would just substitute that in. All right, so I think that's it tonight. You guys have a good evening. I hope to see you back safe in the morning, and go Bearcats!